Okay, we're gonna talk about limits with trig functions, and we're gonna specialize right now in this limit. We're curious on what the limit as theta approaches 0, and you may just want to watch this. You can draw it down. You can draw it out if you want, but probably just watching. It's going to be on the video. Look, why don't we just do this? Pencils down, just laser focus. Ask questions if you need to. Of sine of theta on theta. That guy pops up a lot, and it's a pretty interesting graph. We've already looked at it. If I put 0 into sine, I get sine of 0 is 0, and 0, if theta is 0, I get 0 on 0. So this is across the beams calculus type problem. So this is not a rigorous proof of what sine of theta on theta is, but I think you'll buy it. This is going to be our one building block that we have to work with. We're going to know what sine of theta on theta is. Now, yes, we could go to our calculator and zoom in and zoom in and zoom in and zoom in, or do the trace, and we could do it that way. But I want to go through something that's maybe a little bit more visual. So let's say we've got a unit circle. Unit circle, radius 1. Okay. And I'm just going to draw an angle in here, and I'm going to call that guy theta. At this time, theta is nowhere near 0. Our goal is going to be to talk about it when it gets near 0. Okay. This would be 1. If I draw this down here, can you give me this side in terms of theta? Well, from the angle, that side is the opposite. We know the hypotenuse. So sine of theta equals opposite on hypotenuse, right? But opposite on hypotenuse is on 1. This is the sine of theta over here. Likewise, this down here would be the cosine of theta, but I don't care about it for today. I want to talk about sine of theta. Let's talk about this arc. And I always say this, an arc is just a fraction of the circumference. What fraction are we dealing with? Theta out of 2 pi. That much of the circle. Just theta of it. Out of the entire 2 pi. What is the circumference of this circle? 2 pi r. But r is 1. Therefore, S is just theta. Okay? Let's go back to this. Consider sine of theta on theta. Is sine of theta on theta more or less than 1? If this length is sine of theta and this length is theta. It's less than 1, isn't it? This side's definitely shorter than that, right? And if I go to, say, here, sine of theta comes this side over here, that's longer and longer still. But what happens as I go this way and build that? This arc is still longer than that, but not as dramatically longer, right? What happens when I get into here? Because what's my goal? I want 0 rotation. What happens when I get really, really close to 0? The curve is almost completely out of the picture, isn't it? Have you seen that string art before where there's like nails on the board and you got a string here and you got a string there and you got a string here and you got a string there, and pretty soon it looks like a circle? Those little straight edges, they're basically curves when we get when they get really close together. So that I'm hoping you buy into. Once we get down to 0 here, or right before we get to 0, they are virtually the same length, and everything about them is trying to become the same length. So this becomes 1. This is our building block, and we're going to write that right on the top of our new worksheet. So part B starts out with this. This is kind of a neat one here, called the Sandwich Theorem. And there's another name for it as well, and that is the Squeeze Theorem, and that is not a Hearn term. That you may see it called the Squeeze Theorem. So we need to know that one. Right. So the sandwich theorem says this. It says, if a height of a function is less than or equal to the height of another function, which in turn is less than or equal to the height of another function. So that means all the time, f is at least as tall as g throughout the whole course of the graph, and f is no taller than h. If there's a point on the graph, let's say at C, where the height of g equals the height of h, if this one equals that, and f's at least as big as this, and f's no bigger than that, mustn't f be the same height? Mustn't it be at L as well? Here's a better way of maybe saying that and getting it across. Let's say we've got Bob and Sally and Jim. They all work together. Bob makes at least as much money as Jim. And let's say Bob makes no more money than Sally. Let's say that this is just based on daily pay. And let's say Tuesday, Jim and Sally make $125 apiece. How much did Bob make? Bob makes at least as much as Jim, but no more than Sally. And Jim and Sally made $125 on Tuesday. How much did Bob make on Tuesday? $125, right? There's no room between them. It's squeezed right in between there. There may be a day where Sally makes $2.50 and Bob makes $12 and Jim makes $3. But on that day, if Jim and Sally make $125, Bob had to make $125. I want you to try to, or not try, I want you to graph these, y1, y2, y3. I want you to set x min to be, let's go negative pi, x max to be pi, let's go y min negative 1, and let's go y max 1.5. And graph that guy. And I already have my graph pre-built. It's kind of fun to watch them because it'll go in order. It'll graph sine of theta on theta first, and then cosine of theta, and then just the horizontal line 1. Apologize for the glare. End up with that. And the sine of theta on theta was my blue graph, or the one in between, right? So here's the theory. The theory is, and we haven't proven this yet either, but the theory is, hey, I know that sine of theta on theta is above cosine of theta forever. Now, we haven't talked about that yet, but let's assume we knew that. And most definitely sine of theta on theta has to be below 1. We can talk about that. That one we can express. But if it's always below the black, or not above the black, and never below the red, and the black and red come together, there's our sandwich theorem. There's the squeeze theorem. Okay? We'll use that quite a bit more, not necessarily in this section. But it does show us that that blue curve is getting squeezed through at 1. And that's what we just mentioned, was that, might want to even put it here, it's so big, is that sine of theta on theta's limit as theta approaches 0 is 1. That's huge for us where we're about to go. Alright. Good stuff coming. I'm going to zoom in just a little bit here. Try to zoom in a little bit here. Okay, now, I got all this new fancy stuff, and then they put us right back in a situation, trig functions. I'm not going to try to get fancy here. I'm going to try direct substitution. I put in 0. Well, 1 stays 1, and then I get cosine of 0. I don't have to write the limit anymore because I've substituted in. Well, what is cosine of 0? 1. This is 1 on 1, or just 1. We're done. Nothing to it. My goal is for that to happen all the time, but if that happened all the time, we wouldn't need calculus. Calculus, a huge portion of the beginning calculus is a study of 0 on 0. So, still going to do the same thing. I expect somewhere down the line 0 on 0, but I get 1 plus sine of 0 on 1 plus cosine of 0. 0, not theta. 0, sorry. Habits. Sine of 0 is 0. 1 plus 0. Cosine of 0 is 1. 1/2. That's it. Done. Kind of uninteresting. All right. First thing I'm going to do up here is right at the top, our MVP by far of this section. I'm just going to write it again. The limit as x approaches 0 of sine of x on x is 1. I am completely driven to see sine of x on x. Now, we could probably do some reasoning through this one. If the limit as x approaches 0 of sine of x on x is 1, what do you suppose the limit as x approaches 0 of x on sine of x is? Probably 1. And I think we could make that argument and get away with it. But I'm going to show you, I want you to understand my drive here. My drive is to get sine of x on x, because that's my only rule for this. I can get sine of x on x if I don't change the value of x on sine of x. And I can do that by multiplying by 1 on x over 1 on x. Now, hopefully, after I do a couple of these, there's not going to be any question. And if I do a good job, you won't ask this question. Well, why would you do that? It's not even why. I had to do that. Because all I know is how to handle sine of x on x. So I needed to create sine of x on x here. And all I could do was multiply by 1. So that gives me limit as x approaches 0 of, well, that's kind of nice. I get 1 in the top, and in the bottom I get sine of x on x. And this is my big fraction bar. Here's my little one. All right, remember that big sheet yesterday of our properties of limits? And I said these are exactly what you would guess they would be. In other words, limit of a sum is the sum of the limits. Limit of a difference is the difference of the limits. Limit of a product is the product of the limits. Limit of a quotient is the quotient of the limits. So this is just limit as x approaches 0 of 1 divided by limit of sine of x on x as x approaches 0. You with me? The limit of a quotient, 1 over this, is the limit of the 1 divided by the limit of this. Now here's a tough one. What's the limit as x approaches 0 of 1? What's the graph y equals 1 look like? What's the limit as I get to 0? 1. It's 1. So this is 1 divided by, what's the limit as x approaches 0 of sine of x on x? 1. That's our MVP. Now again, that problem, I think we probably could have made an argument, hey, if the limit of x on sine of x was 1, then the reciprocal should still be the reciprocal. Okay, well, I like seeing this x down here, but that doesn't, this rule doesn't work for this problem. So I either have to figure out a way to turn this into sine of x. Now, sine of 2x, you may remember, may not, is 2 times sine of x times cosine of x. So you might do that and be able to get out of this. But what am I really driven? I'm really driven to have sine of an angle over the angle. And that could be sine of 30 degrees over 30. It wouldn't be degrees, radians. Sine of 0.7 over 0.7. I want sine of pen over pen. I want sine of pen and calculator over pen and calculator. I want sine of 2x over 2x. That's what I want, because x isn't special, it's just an angle. That angle measured in radians has to match this. So I need 2x down here. How could I possibly do that? Well, I'm going to multiply by 2 on 2. So I get limit as x approaches 0 of 2 sine of 2x all on 2x. Think I want to cancel these 2's? That's algebra ping pong. No, I love this 2x. I put it there. So this is limit as x approaches 0 of 2 times limit as x approaches 0 of sine of 2x on 2x. Right? So this could just as easily be 2 over 1 in front. Right? Could just be 2 over 1 times sine of 2x on 2x. What's the limit as x approaches 0 of 2? 2. What's the limit of this? 1, 0. Okay, for you good trig people, here's what happens.
Sorry. This is the answer.
You have the opportunity to be listening to Mr. Kofoid now.
I don't know anything about this math stuff he's trying to teach you now, so.
This is going to be on YouTube, you know.
Is it?
Yeah.
That's great.
For the girls or boys? That's not everybody. This is varsity on the top. Yep. I gave you the cut line for that.
Yeah, I got that.
Okay.
I didn't know if it was both.
I'll stop by.
Okay, thanks.
That'd be great. Okay, for those of you remember your trig identities. This could be limit of 2 sine of x cosine of x. Does that kind of sound familiar? Remember that guy? Sine of x on sine of x on x. That limit as x approaches 0 is 1. So now I have 2 times cosine of 0. 2 times 1, 2. You with me? This one I can chunk out of here because the limit of that's 1. So now I just get 2 times cosine of 0. Okay, so we have options. All right. Yuck. I don't want sine of x. I want sine of x on x. How am I going to put it on x? I'm just going to do it. I'm going to put it on x. I'm going to do that. Now, notice I had another option. I could have factored out an x out of the denominator. But I wanted to emphasize, I don't care about the denominator. I just want this to be on x. So I get limit as x approaches 0 of sine of x on x, love it, over, I'd put this on x, except when I multiply 1 on x times this, I get 2x minus 1. All right? And now I can just take the limit of the numerator and put that over the limit of the denominator. Because that was our rule sheet yesterday. It should do exactly what we want. What's the limit of the numerator? 1. What's the limit of the denominator? Put in 0, and I get 2 times 0 minus 1. So I get 1 on negative 1 or negative 1. Okay? Because the limit of this as x approaches 0 is 1. It's our MVP. It's all we got. It's all we got. We don't have rules about tangent or anything like that yet. Okay? Let's go to G. I know I've skipped E for a reason. We'll come back to it. This is pretty good. But I don't want sine squared of x on x. I want sine of x on x. So I'm going to rewrite this as limit as x approaches 0 of sine of x on x times another sine of x, if you like, on 1. Clearly, those are equal. Right? So this is the limit as x approaches 0 of sine of x on x times the limit as x approaches 0 of sine of x. That's what I was going for. and I get 1 times, I can put 0 in now. Sine of 0 is 0. 1 times 0, that's okay. It's just bad when it's 0 on 0. Okay? So you remember doing trig identities, and you do a trig identity and you feel great about it. You're like, oh man, it took up these 10 steps, and then you'd go in and Mr. Hartz or Mr. Hearn last year would do it in 2 steps. It's like, oh man. Well, and I talked about that, and I said, there's so much wisdom to gain. When you don't gain wisdom from a teacher, you gain it through experience. No wisdom necessary here. I want sine of x on x. That's it. I'm going to do whatever I can to get sine of x on x. I know what the first step is. Last year, trig identities, I made a bad decision on my first step. Maybe I worked it out, but it wasn't the best decision. This year, no problem. I just want sine of x on x. Or I want sine of 4x on 4x. Or I want sine of 3x on 3x. Maybe I could try some way to do it both at the same time, but I'm going to do one of these at a time. I don't believe it makes a difference. I'm going to get this denominator to become sine of 3x on 3x. So I'm going to multiply by 1 on 3x over 1 on 3x. Is it clear why I'm doing that? So limit as x approaches 0, this is 3 sine of 4x all on 3x. Here's my big fraction line over sine of 3x on 3x. Huge payoff there. How many times do you suppose when we're doing these we're going to multiply by 1? We're going to just keep multiplying by 1, getting what we want. So the limit of this is 1. So I would have to divide the limit of this by 1. I do notice my 3's cancel. That's kind of a blessing here, as it turns out. I've got limit as x approaches 0 of my 3's cancel sine of 4x on x. Is that what I want? No, I want sine of 4x on 4x. So I'm going to multiply this guy by 4 on 4. Just make it what I want. There's really no thinking. It's just what I had to have. So, am I going to cancel the 4's? Of course not. I'm going to look at this and say that's 1. So the limit of 4 times the limit of 1, right? Or times 1 is just 4. 4 times 1 or 4. Okay, let's go back to this tangent 2x. I don't want tangents at all. Maybe we'll have a rule about tangents sometimes, but I don't want tangents. I want sines. So to me, first step is crystal clear. Limit as x approaches 0 of sine of 2x on cosine of 2x. Big fraction line. Guys, I'm emphasizing that. If I can't tell which one's the big fraction line, pretty hard to grade. All on 2x. And if you like, I'm going to make that 2x on 1. Because times 2x on 1, or divided by 2x on 1 is the same as times 1 on 2x. So this is limit as x approaches 0 of sine of 2x on cosine of 2x times 1 on 2x, so like that. Anything good happen there? Oh, that's great. I mean, couldn't be any better. I've got this guy right here, and the limit of that is 1. So I've got the limit of that is 1, and then I need, so it's the limit of this guy, I just need divided by the limit cosine of 2x. Is that clear? I mean, I could have treated this like sine of 2x on 2x times 1 on cosine of 2x. Could have treated it that way. Now this is as x approaches 0. What is cosine of 2 times 0? Cosine of 0 is 1. So 1 on 1 or 1. Now's a good time to become a scientist. Let's see, I ended here. I started there. I wonder if tangent follows the same rule as sine. I'm not claiming that's the case yet. You didn't follow that? Because if I put 0 in here, this becomes cosine of 0. Is that all right? If it was 2 times cosine of x, different ball game. We good there? Okay. Pretty good exploration here. I encourage you to do this if you're watching the video. Thanks for joining us today.